This is video 5 in the test 2 review. And in this video we're going to look at taking a set of differential equations and expressing the transfer function relating an input to a response in the system. And I've chosen a problem from actually chapter 3 of the textbook, which we have not even begun on yet. So the assumption is you don't really understand the system. You wouldn't necessarily be able to derive these equations of motion, but the task here is actually to write or define h of s, which is defined as, let's see, theta of s divided by, or actually we'll do x of s over f of s. Okay, what is that? X is the displacement of this cart. Okay, so there's a cart that is this block here that can roll on a guide, and it's attached at the left end by a spring, and there is hanging from below it this pendulum with the mass m2. Okay, so you can imagine that there's going to be some interaction. If you were to let this thing go, the mass 1 would oscillate back and forth, but its oscillation would be affected by the oscillation of the pendulum below it. That we don't really need to know anything about that other than the differential equations that have been provided for us. The input to the system is this external force F. So imagine you are going to somehow apply a force to this system, and you're wondering, how does the displacement of the cart, how does X respond to that force? So our task is to write a transfer function. Okay, so to do that, we're going to take the Laplace transform of each of these equations. Okay, and we'll start with the top one here, m1 plus m2, and we'll take the Laplace transform of x double dot, which is going to give us s squared x of s. And there are initial conditions that would normally be considered, so it would be like minus s x of 0 minus x dot at 0. Okay. However, when we write the transfer function, if you recall, let me go back to what I had shown previously right here. Okay. In general, the response y is going to be the transfer function times the input x plus some initial condition terms divided by the denominator. Now what this problem is that we're solving now is asking for, it's asking for this n over d. It's asking for the transfer function. And so even if there are initial conditions to this problem, they're not going to help us find the transfer function. In fact, they'll get out in the way. So it's best to actually assume that there are no initial conditions. Okay, so we will set these to 0. Okay, they're not needed, not useful in finding h of s. Okay, so back to our first equation. We're now ready for our second term. We'll have m2l s squared theta of s plus k x of s is equal to the Laplace transform of little f, which is capital F of s. So let's rewrite that as m1 plus m2 times s squared plus k, the whole quantity, times x of s plus m2l s squared theta of s is equal to f of s. That's our first equation. Second equation, s squared x of s plus s squared l plus g times theta of s. Now we want to express s in terms of f, and so that first equation is useful, but it has a theta in there. So let's plug this theta into there. We need to isolate theta. So we'll rewrite this as theta is equal to s squared over s squared l plus g times x of s. And now we can plug that into our first equation. So we'll have m1 plus m2 s squared plus k times x of s plus m2 l s squared times s squared over s squared l plus g times x of s, and the whole thing is equal to f of s. All right, so what we can do now, and I will stop here, I don't want to belabor the algebra, but we could write h of s now as being x of s over f of s, where we have 1 over this whole mess here, and then you could do algebra to clean it up. And so that is how you write the transfer function for a system of differential equations. Of course, in this case, it's if you had two variables is easy enough. Going to 3 or more gets more complicated, but the process would remain the same. So just remember that you don't really need to know anything about the physical system, even though it might be described to you. In the end, all you need to know is how to deal with the differential equation to get it into Laplace transform. You need to recognize that you don't need the initial conditions for the transfer function, and then you'll be able to develop the transfer function from the set of differential equations.